Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it is my pleasure and honor to introduce Dr. Shahab Bukai. Our paths have crossed a number of times with profound consequences, really. And we co-founded a startup 15 years back. We were looking at network design and software design for some of the problems he's working on right now. And then he went into academia. He was Dean of School of Science and Engineering. He was the chair of the Computer Science Department at Lahore University of Management Sciences. And right now he's on a sabbatical with University of Illinois at Chicago. And some of the research that he's doing currently, he'll talk about it right now. So without further ado, it's welcome Dr. Bukai to Microsoft Research.
Thank you so much. I hope I have sufficient breadth in the talk to appeal to a disparate audience here and people sitting online, and hopefully they'll be able to get something out of this talk. So the title says Multimedia Communications, an end-to-end perspective. And actually I'll be starting off with some applications. Then I will talk about the basic problem, what we have solved, and I'll interpose this with the work that I do and some of the results that we have achieved there. So primarily I will cover two areas because of the time constraints and others. I don't want to take the whole day trying to tell you about my research for the last decade or so. But I will give you some of the areas that I have looked into and implemented and gotten some results. But the primary emphasis of this talk would be to present to you a basic understanding so that the challenges ahead can be identified. So that's my target for this talk. So, well, ubiquitous multimedia, that is what we have dreamed of. Some of the applications are giving it to us already. If you look, or don't go too far, a decade ago, the things that you would have imagined then are a reality now. Specifically, our GPS combined with mapping and labeling and Google Maps and the like, and Microsoft Maps, the search space, etc. You can have multimodal interfaces. You can talk to a device, your personal assistant, your handheld phone, and run basic queries and those kind of things, which 10 years from now, if you had told me that, yes, researchers were dreaming of those things, but they weren't a reality. Now they are. The computational power in your hand or in your pocket is far beyond the computational powers of servers 20 years ago. When I learned programming, I used punched cards to enter data, and we will get the output the next day, printed on a piece of paper, saying that there was a syntax error at line number 6. So your program did not run. Anyway, so to me, if I just sit back and try and think about where we have come, the progress has been tremendous. But are we there yet? Well, you guys, and me included, because I like to think myself of this generation too, imagine what we could do further, how we can scale up things. If one video on demand application is running, how about 1 million users to that? Is it possible now? Somewhat, but there are constraints. Quality, resource constraints, constraints in how much we can scale up, how many problems we can solve, to what level we can solve. So the challenges are still there. Of course, the nature of those challenges have changed. But I'll try to give you a feel of what are the current challenges in my thought or my mind that needs to be addressed. So this is like a 20 03 map of the world ISP providers. What kind of backbones do they have and things like that, and you can't see it, but just to give you an idea about the growth of the communication medium that we have, which is the primary motivating factor for the info revolution that we are benefiting from today. So multiple areas, design and engineering, CAD, CAM, communications, learning, entertainment, business, all have been impacted by that. Okay, so just as an example application, healthcare application, everybody can appreciate healthcare, right? And typically a cohesive application that has the patient record, the prescriptions, the historical data, as well as the evolution of their health over a period of time. So temporal evolution as well, and some sort of that. Patients, physicians, caregivers, they can all access the data. Maybe in real time, somebody is sitting there at home wearing a sensor, and their ECG is being monitored by physicians all over the world, or expert caregivers somewhere else. Okay, is it possible now? Yes, it is. Is it holistically an application that delivers to the physicians and the customers? No. There is still some work done, most of all in the user interfaces, in the communication medium, in the higher resolution that is required by diagnostics and treatment like that. So are we there yet? Getting there? But of course, there is still something to be desired. Will the result of all this data be available to my health insurance providers? Would my premium go up or down based on my health or health status now, or my health history? What information can I get out of? Could we improve our diagnostic techniques for cancer patients, for example? So a group at LUMS is working with a cancer hospital in Lahore, trying to figure that out and use that as a diagnostic tool, use data mining techniques to enhance the diagnostics procedure that we have over there. Now, let's get into a little bit more complicated scenario. The Department of Defense infrastructure. What are the system features that they envision? At the heart of it all is the communication infrastructure that provides ubiquitous, end-to-end, high bandwidth, high resource service to all applications that require it. And hence, the any place, any time kind of thing at a global scale. So that is what we are looking at, and this is just a collage of various things that they do or they need to do over here. Sensor networks are part of it, and they also form under multimedia communications. Sensors can take or sample the environment, or take real-time video feeds for a certain things that can be analyzed at a remote location, or consumed for some surveillance purposes, or monitoring purposes, or environmental prediction purposes, or any of these combined together. Okay, so critical decisions would require, or are anticipated to require, or wish to have real-time multimedia applications to that. So, like a cardiogram, and multiple doctors coordinating or collaborating together to diagnose a patient maybe just right before open heart surgery, or angiography, or angioplasty. So those are the things that we are looking at. So at the bottom of it, and that is what I do, I try to figure out how to enable multimedia data with the required playout quality, with the required real-time constraints, from one location to a remote destination, one or more remote destinations. And now we have the cloud services, the middle layer that hides the network abstractions or the source or the services, and provides them as a service to the users. So what are the challenges there? Right. So we have this network which is heterogeneous but needs to be interoperable. Video, audio, documents, traditional text, or high resolution video, all that is required to be communicated there, and these are the constraints, or these are my requirements. I require the right quality for the device to play it out, which may not be the same on a handheld as opposed to a tablet, as opposed to a PC. Okay. Security, of course, paramount. I require security at a number of levels. My payload needs to be encrypted. Nobody should be able to hear what I'm saying. Nobody who's not intended for that communication. Of course, I need to decode it and decrypt it to the user. Okay. So unintended participants should not be there. Eavesdropping should not be there. Okay. How do I do that? Sometimes it's just the payload, but at other times I don't even want to know who's talking to who, at what times. So connection establishment or negotiation, or what are the capabilities, what are the codecs that other person can use. Inherently, I want to advertise those. I want to announce this, look, this is my capability, this is what I can use. But I don't want to announce it to other users who can exploit that information. So security at a number of levels. Then I want synchronization. In a cloud, there is an audio server, there is a video server located maybe geographically disparate locations. But there has to be a lip sync between the audio that is coming in and the video that is going out. Like this talk is going out, there may be a different audio server, which is optimized for audio in some way, a different video server. Both have different constraints. Audio requires different bandwidth and latency and jitter requirements. Video is more tolerant to, let's say, jitter or things, but requires higher bandwidth. Different requirements, but they need to be synced together over the same underlying networking infrastructure. And that is what we will be talking about here. How do we accomplish that? Concurrency. I have certain data that is being generated that is available at different locations at the same time. Somebody collaborates over that, changes certain things, who has control over it, those kind of applications. And as an example, this is something that we already see here today. We can go to a map, we can use that map, we can get real-time video feeds, we can look at the street view, we can get the traffic. If there is a crash somewhere, we can get that information real-time and make decisions based on that. Okay? So end-to-end perspective for communication and qualified by multimedia communications is quality management across various systems, across the board. Heterogeneous systems, okay, with different requirements, different constraints. Okay. So we require the networks, the databases, the end systems architecture, the security to all work together to deliver that right experience to the right person at the right time, in the right location. And I can go on with a couple of these things. Okay, challenges. Past, current, and anticipated. Okay? We need to model these documents. We need to figure out what resources to allocate. And if you want to make it cost effective, so resource allocation, because some of the resources would be expensive, has to be done dynamically at the right time to the right user. Okay, so require high bandwidth. Why don't I over provision the network? Why don't I use, instead of a dual core, a quad core machine? So it has to encrypt data, has to require more megaflops, throw more megaflops at the problem. Sure, that is what the service providers were doing initially for multimedia applications. But then there were 1 users, 10 users. What about 1,000 users using the same data or connecting to the same data stream or connecting to the same servers? In the search space, this is what happens. Basically, Microsoft Bing search gets millions of hits. This is just the top of my head figure, right? I'm imagining that they do. Okay, I didn't intentionally use Google here. So, okay. So, we need to model the data and model it in a manner so that the next layer, which is going to talk about efficient clustering, indexing, search kind of techniques, can use that information, which can determine that, okay, at what time do I require what resource. So I need to know the data, I need to model it, I need to figure out what are the deadlines for a video frame to reach the destination for high quality play out so that there is no motion jitter or break in the user experience. Okay, and has to be done in a distributed manner and has to be done somewhere along on the cloud that we have. So network caching and synchronization techniques for this distributed multimedia. Does the network handle it? Does the end system handle it? And there are various ways that people do it. Sometimes in the network, sometimes in an overlay network, sometimes at the application level. Okay. So the first thing is, how do you model the data? So you have various requirements, and now I will talk about synchronization and resource provisioning first, because that is one area that I have investigated in detail on that. Okay, and multimedia communications is coming together of various cross disciplines, as I would call it. You need to know signal processing, you need to know information theory, how to model your source, how to represent your source. So all these codec H.323 or some communication protocol like SIP or H.323 uses at the bottom of the layer, the payload is encoded in a certain manner for efficient transmission. Efficient storage, efficient transmission, are they the same thing? Not necessarily. So they have their own set of requirements. And is source coding and channel coding the same thing? No. And people have been doing it independently doing source coding. At the source, what do you want to do for storage and transmission? You want to remove the redundancy in your information, represent it in a summarized, concise manner so that it requires the minimum amount of resources for a certain quality-based layout. That is what is required. Now, once you put it onto a network, let's say it involves a wireless medium which has a fading channel, or there is bursty packet drop that is possible over here. There, for channel coding, we add redundancy, FEC, FEC, forward error corrections, and those things. What do they do? At a higher abstraction level, if I take the top-down view of it, they are adding redundancy to the data so that if I lose certain amount of data, I can reconstruct it from adjacent data. Right? So hang on. Source coding, removing redundancy. Channel coding, adding redundancy independently. So what researchers said, okay, let's marry them together. Let's, for a more optimized, more efficient representation. But then I have to encode my, let's say, video to be transmitted over a high quality link versus a wireless link separately. How do I handle that? Do I have 10 different encodings stored there? Or in real time, do I cater for 10 different encoding, or are they negotiated real time? People came up with scalable video encoding. For different heterogeneous platforms, you encode it in layers. So you get more layers for higher quality, you get less layers for lower quality. Overhead, yes, there is a little negotiating overhead, but tolerable negotiating overhead. So we have scalable video coding there. So source coding. And how do we model the data to encapsulate all of this? That, okay, if I'm doing a video along with audio, lip synchronization has a delay requirement of 80 milliseconds. If I go beyond that, then real-time conversation breaks down. Okay, so people do work in understanding and evaluating the quality of various media, independent or jointly. So I will call them as interstream and intrastream. Intrastream means within the stream itself. There's a video scene, what is the quality requirement there? What is the spatial frame size? What is the frames per second that I need? Is it HD quality, NTSC, PAL, or QCIF? Now, those are just names about different quality of video, just video. But interstream would mean video and audio. Audio is coded using MP3, let's say codec. These are names of codec in case, and please feel free to interrupt me at any time. Okay, so I need to model this data. So what modeling methods do we do? So I need models for spatiotemporal synchronization, content representation, quality attributes, access, and so many other features, and I just come up with a list. What are the models available out there? Language-based model, SGML, XML now, object-oriented models, graphical models. I have worked on, so this is the example of a browsing graph, and a dynamic browsing graph, which let's look at a certain time frame about that browsing graph. And I see that there is audio in there, there is text, video interposed with certain synchronization requirements. And of course, the bandwidth profile, and so I'm just looking at what kind of bandwidth do they require, is a varying bandwidth profile. Whenever I have video along with audio, that is the highest bandwidth or capacity that I would require for a network to efficiently carry it from one point to the other. And that is what I'm looking at, right? So I need to know this so that I can efficiently allocate resources in real time to this. Rather than, okay, I can say, okay, this is the capacity, the top capacity that I require, fine. Let me give it that capacity. Fine, I can do it to 1 connection, I can do it to 100 connection maybe, but what about 1,000,000 connections? My network would say, no more. And that's where I get denial of service. Or I need to apply access control. Okay, so many users logged in, sorry, service is busy, come back and watch this video another time. And we all know what happens then. Of course, we never go back and watch the video again. Okay, so content at the right time that I require it, if I don't get it, it doesn't serve my purpose. Okay, so I have worked on a model called the Petri net model, and I call it the object composition Petri nets. I was part of a group that worked with this model and talked about modeling the experience, the multimedia presentation. Okay, and then how do we provision it for networks? So we have various things like that, that this is a video, what quality, what codec, but that is going too fine grained there. So I'll restrict it there. So how do I use this? I use this in a database schema. I use it for access control, for security, for storage, management, I/O scheduling, end-to-end synchronization protocol for my networks. Okay, so what do? I have this metadata, and so I have modeled it now, right? I need it in my network for my OS, for my database, for my security, and I adjust the quality of service of each of those components. Usually quality of service is associated with networks, what it can give you, what is the delay, latency, capacity, bandwidth, burstiness that a network can handle, right? But I expand it for the sake of conversation and talk about OS, databases, and security, right? And then I do something. Then I say, okay, now I can do resource management. Because I know the profile of my data, I know its traffic requirement, its reliability requirements, its synchronization requirement. So now I can play with those. Thanks. Okay. So this is an architecture that we talk about, that this is the network part, and we are talking about, remember, multimedia communications. How do we enable it? So this is the, let's say, the network layer, the routing and allocation, the synchronization layer, the configuration management, information, location, identification, and the application layer. Of course, this is just an abstraction for us trying to understand the various functionalities that is required. In applications of today, for example, let's pick up a typical application that everyone is familiar with, Skype. Where does what happen? At the application layer level, most of the things, right? Skype is an application that establishes a connection and looks for a supernode and then figures out NAT versus PAT translations and uses stun to do that, and then goes through a firewall, establishes a connection, selects a codec, and at the other end, and there are various presence indicators and things like that. So all those things, and the OS, the database, the storage, in some distributed fashion provides that for that application. Okay, so basically, how do I determine the resources now? Because I now have the model, and I need to map those resources on top of that model, or using that model, and provide that. So at the top, I'll introduce another term called quality of presentation. What I specify, the synchronization, the frame rate, the buffer sizes that are required for that, as these are my presentation requirements. And what the service provider can provide, the network can provide, is called the quality of service. So I need a first mapping there. And then I need to talk about end-to-end resource allocation. And I say end-to-end because internet or our packet switch networks is a hop-to-hop network provision. Basic network architects traditionally used to say that all data is treated equally. You give me a data, I will try my best effort to take it to the destination. And of course, there is a networking architecture, a layer architecture that does that for us, right? And now we have this multimedia data, and like for network architects like myself who work in the multimedia domain, we say that not all data is equal. Some has higher priority, other, if I lose it, fine, I can still manage. So we talk about those things, and I have worked in the area of how do you manage graceful degradation in a resource constrained environment. Let's say you wanted 30 frames per second video with a certain NTSC resolution, okay? But you say, okay, I can't have it because I don't have enough resources for it. Can I settle for a 24 frames per second video? Yes, I can, maybe, right? So there has to be this kind of negotiation, renegotiation that can happen. But if I lose a packet in the middle and it is MPEG 2 encoded or MPEG 4 encoded video or H.264 encoded video, I can throw other names here also. If I lose some data, how is it going to impact my group of pictures, my slice layer, or my macro blocks, or my motion vectors? Those are the things that are used inside H.264 encoding. So I need to have an understanding of that. So not all data is equal there, right? Some data, if you lose that, I lose a group of pictures, I lose a whole frame. Other data that I lose, the same comparable fraction of data. I just lose a macro block and I see a black spot in the middle of a frame that is played out 1/30th of a second. So the quality appreciation for that loss goes from one end of the spectrum to the other, right? So I have to figure that out, right? And we need to do it intelligently. So all data is equal? Not really, okay? So we have to do, and we can exploit that or leverage that information and design certain protocols and things that, okay, so constrained environment, we have to degrade our performance or play out, but how to do it in a manner which is least likely to impact an application. So that's an area of research also, and resource scheduling we talk about. And finally, synchronization. So the thing that I'll go into a little bit more detail is end-to-end resource allocation. I've worked on this part also, but maybe for another time. And after this, I'll go into the security aspect of things, which is, in my opinion, one of the most paramount or most impactful things that we have to do today. We have to convey multimedia information reliably and securely, okay? So I believe that that is an area of research for specifically for multimedia, and how do we leverage our knowledge of encryption, cryptographic techniques, and apply them efficiently for multimedia traffic. Okay, so I'll investigate that part also and present a little bit of my work to you over there. Okay, so let's think of a black box approach. This is a source, that's a destination. In between we have a network, of course, a hop to hop, or has resource reservation techniques, RSVP, or those are old techniques, or an MPLS provisioned virtual path that provides a certain degree of bandwidth, a certain latency, a bounded latency and a bounded jitter, and that is what our quality of service is. So possible quality of presentation parameters used to formulate end-to-end resource allocation problem: jitter, delay, synchronization, reliability, bandwidth, right? Those are our parameters that we use. So if I abstract the communication and I have multiple servers in the cloud somewhere, right? I have a network, and then I have various paths that traffic would take. Could be the same path for the entire flow, like an MPLS, or could be like a path for each packet, like the internet abstraction. Okay. So the problem like that we have worked on, and there are other objective functions, but there is one objective function. We say, let's talk about reliability. Let's how do we reliably take this information and make it available to the next, to the destination, okay, end to end. So we talk about, let's look at capacity, for example. We require a certain bandwidth, and we have looked at the bandwidth profile, the time varying bandwidth profile, that ultimately we need to dynamically allocate our resources to match that, okay. So these are certain parameters that we have, n objects that need to be transported, n could be large, and if it is larger, then it's a bigger computationally harder problem to solve. So this is, we have the bandwidth requirement for each object that is specified to us in the model. We have the reliability requirement of each of those objects. So the total capacity requirement at a given instant in the presentation would be, let's say, gamma, that is the sum of all requirements of these simultaneous objects that we need to transport. Simple. Okay. If gamma is greater than the available capacity, right? So certain degradation has to take place, right? How do we do it gracefully? So this is the theta I is the percentage of the data that has to be dropped from each object, okay? And how do we determine theta I for each component? Not all data is equal, okay? But let's simplify the problem for the scope of this talk, okay? Let's say, okay, we want to, let's say we say that, okay, we will use an objective function of fairness across all objects. Let's say all objects were video objects, right? And let's not get into the issue of our disparate objects. And we say that in accordance with their reliability requirements, we want to distribute the penalty on that. And we formulate that like a non-linear programming problem, NLP, and we have ways and means to solve an NLP problem. So we say, okay, let's talk about the network and figure out that there is the path, then there is the CPU cycles that need to be allocated, resources. So the network, the CPU, the storage part, and this is, let's say, the theta I L K is the amount of penalty that is going to be imposed at each link in an end-to-end connection. Okay, so we can formulate this like a NLP problem with these objectives, where we want to minimize the mean square penalty, okay, or distribute it justifiably across all the objects. Okay, so that's an objective function. We can change that if depending on our requirements, right? So this is like minimization problem that is set up, and this is like a flow chart about all of these. So allocate I/O capacity by solving the NLP, which talks about I/O penalty, okay, then link penalty, and then if there is an alternate path that needs to be selected for that, or if it is available. And if all of these are satisfied, the non-linear problem that we formulated before, then we accept the connection. So this is like admission control, saying, okay, for this connection which would have that traffic profile that we have modeled, can we provision it? Okay, and we do it, and then we go to the next decision point. And so what are the decision points in the time varying requirement that we have for capacity, because that is what we are looking at right now, the bandwidth. Okay, so these are our transitions levels, that at what point does our requirement change, and that is how we proceed with this. And so at these points we have to solve an NLP problem, but then we can do a trade-off. We can say, okay, because we don't want to be solving the NLP problem at each of these transition points, right? So we can do a coarse-grained resource allocation, and it would follow something like this here. If there is a significant change in the bandwidth, then we will solve the NLP problem and allocate resources accordingly. Okay, so this is one of the aspects that I looked at, and I have looked at, and things like that. And I've simplified the problem here just so that I can tell you what all is required in resource management part of it. Then comes synchronization, then comes other factors as well of making a cohesive application that involves multimodal inputs. Okay, so the second part of this talk, any questions there? I should give you an opportunity to ask questions. If there are any remote people, can they call in and talk?
They can.
Okay.
Yeah, they can send in.
Formulate a question to you.
And I can pose it.
How are we doing for time?
Okay.
Okay. No questions? Maybe I simplified it too much, or everything is real clear. And well, the fact is that all of us have thought about this, or have been impacted by some sort of degradation, quality constraints in the network while using certain applications. I believe that all of us have, either watching a movie at Netflix or using conferencing software, or I don't know if you guys remember the first adaptable protocol came out of rail audio. There was this rail audio thing, but I don't see it anymore, things like that. And what used to happen there was that you start getting, when you request a connection, it will say calculating buffer. So it was dynamically allocating resources. And it tried to send out probes and get the current network capability of performance, and that's a challenge in itself. How do you estimate the current network bandwidth and project it for the next allocation? So, and there are various factors that can impact dynamically on that prediction. So that, so it used to calculate that buffer and start a presentation, but the network's congestion or characteristic would change. And then it would say, it would hold the presentation and say recalculating buffer. Okay. Now, the applications don't report it to you, but they still try to do the same thing and try to do it adaptively in a manner so that any degradation is hidden from the consumer. Okay, so that's a challenge within itself. How do you conceal errors without degrading the resolution, the quality, the playout, the color, or whatever? Whatever are my quality of presentation criteria. Okay, so now I'll switch tracks and I'll talk about encryption. And what I will talk about is selective encryption. All of us know cryptography, or all of us know about the keys and exchange. I'm assuming that here because I'm sitting or I'm talking to a very enlightened audience, I believe. So, and all of these things we use on a daily basis. We do establish a secure connection using TLS, transport layer security, or IPsec, and we know that there are passwords in the clear on NTLM, on those kind of authentication, Kerberos, and those kind of things like that. So, let's talk about security attacks on the internet, and you'll notice a shift in the presentation style, because this is a presentation that I prepared or that I have used or reused from another conference. So let's say we have this internet and there are various applications, some of them are out there that try and get or eavesdrop or secure certain information or obtain certain information to which is not directly addressed or available for them. Okay, but it is available out there, it is available in the network, and they want to get this information. And this is possible because initially when the network design was made, so we didn't think about security that much. But slowly and gradually we evolved to realize that this is an important concern there, like that. So no longer can be done in the open. We need security because our critical applications are out there, our business transactions are out there, our bank accounts, our credit card information on an individual scale, and on a larger scale, sensitive information that we don't want everybody to access. Okay, so what we do is we use various techniques like that secure these at different levels. Okay, so have become the de facto standard. Like I was saying, that I'm assuming that everybody has used them at some point or the other, like that. What about multimedia support? I deal with multimedia, so I say, okay, we need to secure everything. And how do we do it there? Well, multimedia, as we saw in, and I wanted to convey to you also, has different requirements for different media types, but they are definitely more constrained than for, let's say, traditional textual data. There is a timing constraint, there is a reliability constraint, there is that certain information, if you lose, the impact on quality is very profound. So how do you address that? So there is a significant overhead to it if I apply traditional security protocols on multimedia traffic. And multimedia streams, let's say it's a 1 hour long stream, so let's say about a 30% computational overhead, which is the top of the head prediction for traditional security or encryption methodology. So 30% overhead over a 1 hour period is significant overhead. Can we do better? Can we minimize that in terms of computation, in terms of network footprint, in terms of latency? So we would like to be able to do that. Okay. So we know that there is a high overhead. There is the bandwidth constraint that we have. There is a constraint on latency and jitter that we have. But security protocols that were available out there impose all of these, and they impact the quality of multimedia presentation. So we would like to do something about it. Okay. So we can talk about faster hardware, use proprietary protocols, or selective encryption. So I will concentrate on selective encryption, basically intelligently secure some data which will give me equivalent privacy that I could have obtained by applying the traditional ciphers to the entire stream. Okay? And I would like to do that in a manner that minimizes the CPU, the network overhead, and the latency that is incurred while doing encryption. Okay, so this is what I will talk about here. So to me it seems like the best option because of my unwavering belief that not all data is equal, especially in multimedia traffic. Okay, some data is more critical to the decoding process, to the playout process than other type of data. Okay, and to the deciphering process as well. When I want to decode something, if there is some data in the clear which does not give me much, I can treat it like noise, or I can evaluate whether I can treat it like noise. Okay, so let's look at a typical VPN. Where does the overhead come from? So let's say this is a private network that needs to communicate over the internet in some secure manner. The usual data link layer, the network layer, and on top of it the transport layer. Of course, application layer sits way on the top. Okay, so the virtual networking interface, which enables us to establish a VLAN type of configuration or VPN configuration, sits along with this there, and basically we have a control plane for it. We need to do a key exchange for it, and so that information goes out there, public, private key, etc., depending on what sort of algorithms am I going to follow. And this is the data plane where I have to the information is compressed, encrypted, and authentication. So those are the tasks that are performed in the data plane there. From a private network, there is a data that comes in, goes through that, or is rerouted through that, rather than just going directly from the network layer to the transport layer. And the VPN daemon performs the compression, encryption, authentication mechanisms there, and then goes through the TCP stack or the transport stack, network stack, to the Ethernet out there. Okay, so we want to make this more efficient. For multimedia traffic, why multimedia traffic? Because multimedia traffic is isochronous. There is a stream that requires high bandwidth, low latency, low jitter, bounded jitter type of communications for an extended period of time, right? So we want to do that. So we observe that multimedia documents exist in the compressed form because we want to make their representation more efficient, or storage more efficient, or transport more efficient. Okay, these are the example of the codecs that are there: MPEG, OGG, Vorbis, or Theora, H.264. All these are all compression standards or codecs, compression decompression standard. Okay, they have a property that what does compression do? How do I reduce redundancy from the data? I concentrate important information into with a smaller footprint, storage or network, and I devise a way of encoding and decoding it reliably. Okay, and so I can talk about lossless or I can talk about lossy, but all compression techniques want to do that here. So, for example, the OGG standard, which is the wrapper standard, and the Vorbis files have specific decoding information only in the first 100 bytes, and the rest of that is encrypted or is compressed information that I can, if that only that is available without the headers, I will not be able to decode it effectively. But we want to discover how effectively. If I just hide the first 100 bits and let the other bits go in the clear, what happens then? And this is what we have investigated, and I will use the G729 codec, which is the most widely used codec in audio communications, as a representative example for it here. So if there are errors in the chunks, like from attackers, or imagining that if those chunks are destroyed, they may make the decoding process impossible. We want to evaluate how impossible. What is the data in each of the compression standards that is so critical that without which we will not be able to decode that information, or the information is so degraded that I will not be able to make sufficient or gather sufficient or interpretation, attach any interpretation to that data. So this is what I want to evaluate there. So there is a difference between looking at degradation or deterioration or from hiding some of the information versus the quality of presentation that I was talking about in the first part of this presentation or this talk. There I was saying that, okay, if certain degradation has to occur, I try and hide it or minimize it and still present the data. So maybe I see a noisy frame, but I can still make out if it is a house, if it is a car, or if it is a person, or is it day or is it night, right? From a security perspective, I want to introduce sufficient distortion that removes all contextual interpretation from the data. So an encrypted stream, I should not be able to get any information, not just a deteriorated or a noisy image, but I want to hide the data completely, right? So that's my target. So when I talk about quality, that's from a different perspective. It's the same, trying to hide the data or the data is lost. But from a quality perspective, I'm trying to minimize the degradation. From a security perspective, I'm trying to hide the interpretation of the data without the necessary key or the decoding process that we have here. Okay, so I want to make the decoding impossible without my key. Okay, so the success of these schemes depend on the amount of data that needs to be secured. If it is substantially smaller, then I will get certain gains out of it. The processing cycles that need to be allocated for the encryption and the subsequent decryption would be less, the latency would be less, the network footprint or the overhead of this would be less. Okay, and I need to prove that the privacy is preserved. That's the hard part. Provable security is the hard part to do. Okay, so what I will do is I will say, okay, let me simulate certain attacks, and I will say, okay, what is the information that I got out of it? Okay, so we'll see that, and I'll try to keep it concise and not bore you with too many details. So the objectives are that this security or this sort of encryption or data hiding should be effective, efficient, practical, economical, and privacy should be ensured. Overall, all of this. Performance should not be compromised. Okay, design architecture coding requirements should not involve major functional changes, because if I have to implement major functional changes, who will adopt it? Unless there is some significant gain out of there. So it should be standards compliant in some way. Okay. Cheaper than the cost of program being secured. If I want to try and hide the information, and the cost of securing that information, the resources that I allocate are so significant that who cares what I talk, right? Paradigm. So, well, of course, I care, you care what I talk. Okay. Anyway, so let's talk about voice communication, because a representative example would be from the audio compression standards, G729 codec. So PSTN calls are inherently secured. The public switch telephone network, for those of us who don't know what PSTN stands for, it's a connection-oriented infrastructure. A physical connection is established, and all the connections are owned by the telco. If anybody snoops on that, it's the telco itself that can monitor calls and things like that. So let us assume that that's not happening. So, but when we talk about voice over IP or over IP communication, packet switch communication over a public infrastructure like the internet, then I want to secure the voice and video calls over there. Of course, I can secure the entire stream using the very robust encryption standards that are out there, like RSA or other algorithms that are out there. But what I have tried to construct is a need for scalable partial encryption. Okay, so let's look at the typical call establishment in a SIP scenario. SIP is one of the session initiation protocol, is one of the most widely used call establishment procedures, open source procedures that are out there. So if a user wants to establish a call through the public network to another user, okay, sends a SIP request, depending whether the voice over IP server is acting as a proxy or it just facilitates presence monitoring and things like that. The request goes there, goes to the user. The user translation takes place through the SIP. There is a phone number associated with each user that can be dialed, and the server knows about it. The user accepts the call. Some codec negotiations take place using SDP, session descriptor protocol. The request is established, and then payload data takes place. Very simplified, very simple for the purposes of understanding. This is what happens there. Okay, and so my interest is right now to secure this part. Of course, who is talking to who? When are they talking about that? That is an important consideration as well. I want to hide that too. But let's leave it for another time there and make things simple. Payload only. Okay. So let's look at one of the most widely used codec, G729. Why is it the most widely used codec? It has about 6 to 10 kilohertz, kilobits per second network footprint, low complexity, has real-time implementations available out there. Of course, they do demand a certain royalty associated with it, and has office quality voice or toll quality voice. For telephonic conversation, this is fine. This is not a high fidelity codec, but for voice over IP communication, this is the most widely used codec out there. Okay. Of course, there are wideband codecs as well as narrowband codecs out there also. But so I decided to use this as an example. We had worked with other codecs as well, and I'll talk. While summing up this talk, I'll talk about what's out there. What are the next steps there? So what this codec is, it takes a 10 millisecond sample and so audio frames of 10 milliseconds corresponds to 80 samples. Okay, so that's the sampling there. And if I look at the codec or the bit allocation in the G.729 stream, so I talk about that 0 to 64 bits. What are the parameters that are being encoded over there? So the first step is to identify what are the important parameters that are required to decode this or to reconstruct an audio signal, decompress audio bit stream that is compressed using this codec. Okay, so that is the first step. There were two approaches that were proposed for encrypting this in a partial manner, and they identified, this is Cervetti and DeMartin, they identified that if we do 45% of, or if we secure 45% of this data, this is equivalent to full encryption. If I encode all of the bit stream. 45%, yes, 50% gain, 55% gain in that, that's good. Okay, and they said, okay, if we secure 30% of that, so it removes the understanding of the speech. I can still probably make out that the speaker is a male or a female, or the pitch of that, or when there has been a pause in the speech, but I cannot understand what is being spoken to. So sometimes there's just this requirement that all I need to do is to hide the intelligible speech, okay, but not worry about the pauses or things like that and other information that can be extracted from a speech signal. So 30%, not bad, okay. So and they identified that each bit of the packet that is contained there, said 64 bits, the 10 millisecond samples there, corresponds to what mean opinion score value. This is how do you measure the quality of the voice call. Okay, and they decided, okay, that if I remove this, there is this impact, and if I have encode that bit, then what happens? Okay, so another work that was done by Hei Yang, and they have a patented codec out there that has 5 levels of encryption, selective encryption, and they evaluate that what do they hide and how much encryption do you do with that. So we said, okay, like, can we use their work and use that? So 2 levels of protection in this, Cervetti and DeMartin, 5 levels of protection over there. Actually, these 2 levels correspond to a class 3 and a class 2 compression or equivalent privacy that way. Can we do better? So we said, okay, let's, and our result, or what we did, we said, okay, only encrypt 5% of the content rather than the 45%, the 30%, and the various. So, and we based it on direct hash mapping shuffling and shuffling the key changes after each of 8 G729 frames. Okay, so using this and exchanging the encrypted hash table with under some secure mechanism enables us to do 5% of encrypting, 5% content encrypting that much and getting, we claim, equivalent privacy of full encryption. So to us that is a significant impact of that. Okay, so I'll talk about what are the important fields and unimportant fields that we have experimented with and identified. So this is just a listing of that. I can go back and talk about each of these. They correspond to the pitch, the PCM samples, and the tone of the encryption there. So we said that these fields are important, these fields are unimportant. Okay, and if we look at that all these fields on this side are unimportant, these are very important and medium important fields that we have over here. So what's our encryption technique over here? We buffer these frames because we collect a number of frames so that we have sufficient data, otherwise brute force attack would work. If I have only 8 bits to compress, then there are only 256 combinations. Okay, so I need a payload size. But that payload size, or I should not be buffering so many frames that they correspond to, remember, if I have a lip sync synchronization requirement, so my latency cannot exceed 80 milliseconds. So so I have to talk about how many frames to buffer so that it doesn't impact the quality of the application or voice quality of the application. Extract critical and non-critical data out of it, the ones that we have talked about and identified. And we do the hash table lookup and shuffling of that, so that to diffuse the information over the entire stream so that it becomes unintelligent Okay, so we get the G729 audio streaming. This is the streaming stack. This is the 8 samples, 80 bit each, that we group together, and this is our encryption or batch encryption that we do. So 640 bits, give them to the splitter, split the critical, non-critical fields, okay, and we take the critical fields from there, okay, and we do a hash table shuffling, and basically we give it to the standard AES encryption, okay, and then reassemble the bit stream to be standard compliant. Okay, so this is the first step, the second step, third, and the fourth step. Okay, in phase 1. Okay, in the next phase, we take that, so the critical fields are now AES encrypted. The rest of them are in the clear. Okay, the stream is reassembled, or those 8 samples are reassembled in the 640 bits to conform to the standard. Okay, and then we do a hash-based shuffler. Okay, with a certain key that is extracted from the non-critical bits. Okay, and of course, and the key changes because those non-critical bits which are going to treat like noise, because if they are available out there, they will not contribute to the deciphering or the intelligibility of the bit stream. Okay, and these are the shuffle bits which are given to the assembler, and that output is gone and transmitted. Okay, so phase 1, 2, 3 in the second phase, okay, and given to the transport layer. Okay, so this requires the following information to decode each set of 8 frames. It requires a 256-bit key that I extracted from the unimportant bits which are transmitted in the clear. Okay, 304-byte long entry of the hash table, and the decryption of the 32-bit selectively encrypted partial data in the important fields. AES encryption, I need to decrypt those. Okay, and I use a standard encryption or cipher to secure that. So which means that the strength of the cipher is now dependent on that, and the extraction of the 256-bit key of that. Okay, so and we said, okay, how do we verify that this is provable security? So we set up a test bed of 3 servers, one located in Washington DC, one located in Chicago, and one located in Lahore, and used a voice over IP implementation, used Asterisk for that, and established a long bit stream through that. And through the 3 legs, we monitored the stream by the selective encryption, and we tried to simulate the insider attack, the packet sniffer, the man in the middle attack, and using those we set, and we did a brute force analysis to that. So the key maps to the hash table changes every 8 G.79 frames. The shuffling pattern stored in the hash table will require exploring of 304 factorial permutations, very large number. Okay, the attacker requires 2 raised to power 1400 to perform brute force. Right? So brute force attack is fine. Yeah. This is equal, but or rather better than full encryption. But of course, we can do full encryption using the same technique and claim the same results. Okay. So this is the thing that we did with partial security or selective encryption. But we didn't just stop there, because now, as I demonstrated, G.729 codecs, certain important fields are there in the bit stream. What about G726 codec? What about speaks? What about other audio codecs? What about video? So for each codec, we will have a selective encryption scheme, like a library of algorithms. So just like a user goes and negotiates a codec, that okay, I'm using or my capability is G729, G726, G721, A-law, mu-law, what is yours? Okay, we agree on a certain codec, or we transcribe, or we have a gatekeeper somewhere in the middle that translates one codec to the other. Okay, so we negotiate that. So at the same time, do we also negotiate a security associated with that and communicate that? But that is sending out too much information. So our next step was to investigate and explore what are the commonalities in that, and can we find certain information which is critical to the decoding process, which is common to all codecs. And yes, we did. And what is that? Entropy encoding. All of the compression standards at some point or the other employ entropy encoders, like arithmetic coders, Huffman encoders, and those kind of things. So securing the decoding process of that, or diffusing the information available in the decoding process of that, gives us across the board there, and there is some work that we have published associated with that also. Not just that. What does RTSP do? It secures the real-time transport protocol stream. And in multimedia communication, either RTP or OGG or some such wrapper stream is used to give us the synchronization, the bandwidth utilization, the quality of experience, RTP along with RTCP. Okay? So if we do RTSP, so we can secure the payload. But can we do partial RTSP? And the answer is yes. Using the same thing, we identify those bits that are common to all RTSP or RTP streams, and assuming either RTP or OGG, so we have reduced the variations that we need to do to secure or give a holistic security mechanism, which is more efficient and is easily mapped to some of the heterogeneous devices out there. Because we have, like from the handheld devices to the large devices, we have all these with different computational network constraints. And we would like to map all these algorithms to those, right? And the final thing is, the advantage that we get is less power consumption. Because less computational overhead, less power overhead. And that is very critical in certain applications. Okay, so just winding up, I just gave you 2 samples of my work in multimedia communications. So multimedia communication, I do other work also. Network resource management, I posed a very simple problem and presented it to you. Hopefully you all understood it and appreciated that a little bit. I do scheduling of synchronized delivery as source-based scheduling, and what happens in the network. How does that network or next generation networks which have intelligent processing and storage mechanisms in there, like the CCN, content centric networks that are some of, or one of the initiatives by NSF to develop next generation networks. How does these protocols or this architecture or this enabling multimedia translate to those networks like that? What are the resource management constraints and requirements, and how can we leverage this on the next generation networks there? So security and graceful degradation. So they kind of are the different areas that I investigate in multimedia communication. And recently in my sabbatical, I'm exploring semantic or attaching meaning to video and audio, like activity classification, recognition, and using those or motion-based cues to index and retrieve or classify activities in a video sequence, especially applied to surveillance videos. So with that, I wind up my talk, and any questions? Thank you in Urdu. That's my language, and not any questions. So if there are any questions, please go ahead.
Questions. So you were mentioning the certain bits in encryption. Mm-hmm. So I assume those bits exist in sort of every packet or a block of packets.
Yes.
Because if you were doing a packet level selective encryption, then I would assume that a differential analysis would expose at least some content.
Right. So in cryptanalysis, and we have done that too, but I just didn't show the results. There is linear cryptanalysis and differential cryptanalysis. And so what is the statistical information that you can get out of that? So and that is why the key shuffling that needs to happen to diffuse the pattern. And good encryption or ciphers are the one that if I take the same stream multiple times, I will get a different diffuse stream. Right? And that defeats the differential cryptanalysis that we have to show. Otherwise, we can extract a pattern out of them. And as I said, that these are long duration streams, or if they are long duration streams, they last 30 minutes, then 25 minutes later I can extract a pattern and decode the 26-minute stream there. But because we shuffle the key and the results are not the same pattern every time because the key shuffles.
Okay. That leads to my next question, which is what happens to packet loss then?
Okay.
Because now if you start losing.
Right. And so if you lose a packet, which is the aid collection of that, and how do you recover out of it? So from those 8 bits, this is something that we haven't investigated too far, but you lose all the 8 samples because they are grouped together and ciphered together. So if you lose the important part, packet loss, bursty traffic characteristics or fading channels, and you lose that, so that is something that we will be investigating further, because we have done graceful degradation and talked about bursty packet loss or relay fading channels and those things. If you lose a packet, how do you recover out of it? So you spread your information or you shuffle your information so that successive packet losses does not impact, or the degradation is graceful. So that's the work that I didn't present here, but we haven't applied to encryption yet. So we will. Thank you.
So you assume that the whole packet will be there at the end.
Right. All 8 samples.
8 samples.
Right. Because then you will decode that and the next phase. But like I want to be able to do better. And can I do better? The answer is yes, I can do better by shuffling some of the header packets with the data. But I just wanted, or right now we wanted to be standards compliant. Anybody looking at that stream would see a G.729 encoded stream. Just will not be able to decrypt it. Okay.
I have a question about the selection of critical and non-critical data within the stream. And my insight is it is more related to the codec that you are
Yes, it is.
doing. But do you have any suggestion of what kind of data becomes critical and what kind of...
Okay. Okay. So, for example, in audio, the PCM samples, the pitch, and this would be different for speaks and G.729. So for video, it is entirely different. And for example, in video, because I do more work in video and my collaborators do work in audio, if you hide the DC level in a macro block, because most of the energy is concentrated there, codec specific. So for H.264 codecs or the MPEG to revision 10 codecs, so those macro blocks DC level is critical to the decoding of the macro block, right? But if you hide that, you can still get some edges, and we humans are very good at interpretation. So we can know it is a tree or a texture or a house and those kind of things. So and the work that we have done on video codecs revolves around playing with the entropy fields or the RTP fields that you do not, or you are not able to decrypt the payload in an RTP stream. Okay, by hiding the RTP headers or scrambling those headers in a way that lets you lose synchronization and recoverability of that stream, but in a manner that we can or the intended recipient should be able to. Of course, there are all those other factors that I didn't cover here. How do you do the key exchange without compromising the key? Or how do you exchange the hash table without compromising the key? So over here we are assuming that we are using standard public-private key encryption to do that, right? And we do it once and we go to the next step. Okay. So there are details in all of this that I'm happy to share and refer you to our publications in case you are interested in this.
Okay. Well, let's thank the speaker. Thank you very much.
Thank you very much for taking the time.